Hello and welcome to this math lesson on real-life application of derivative of functions. Today, we'll explore how to use derivatives to solve real-life problems such as fencing a rectangular lot and designing a cost-effective box for a food business. By the end of this lesson, you'll understand how to maximize an area given a fixed perimeter and minimize cost when designing a box. Let's start with our first real life scenario. In this problem, we are asked to fence a rectangular lot to maximize the area for a vegetable garden. We have 200 meters of fencing material available. Our goal is to determine the dimensions of the garden that will give you the largest possible area. To solve this problem, let's define our variables. Let x represent the width of the rectangle and y represent the length. Since we want to maximize the area of the garden, we'll use the formula for the area of a rectangle, which is A equals X, Y. This is our optimization equation. We're given 200 meters of fencing for the lot, which mathematically means the perimeter of the rectangular lot is 200 meters. So we can set up a constraint equation for the perimeter. The formula for the perimeter of rectangle is 200 equals 2x plus 2y. Subtracting 2x from both sides, we will have 200 minus 2x equals 2y. Dividing all throughout by 2, we get 100 minus x equals y. This equation expresses y in terms of x, which will help us express the optimization equation in one variable. Substituting, we will have A equals x times the quantity 100 minus x. Applying the distributive property of multiplication, we get A equals 100x minus x squared. This is our function to maximize, where the area depends on the width x. To find the value of x that maximizes the area, we take the derivative of the area function with respect to x and set it to 0. To do this, we apply the rule for differentiation. F prime of x equals u prime minus v prime when f of x is equal to u minus v. Hence, the derivative is 100 minus 2x. Setting this equal to 0 gives 0 equals 100 minus 2x. Solving for x, we find x equals 50. We now check whether the maximum value of the function occurs at x equals 50 using the second derivative test. In the second derivative test, we have the following conditions. First, if the second derivative of the function is greater than 0, then the function has a relative minimum value at x equals c. Second, if the second derivative of the function is less than 0, then the function has a relative maximum value at x equals c. Getting the second derivative of the function in our problem, we get a double prime equals 0 minus 2. Simplifying, we will have a double prime equals negative 2. Since a double prime is less than 0, we can say that the maximum value of the function a equals 100x minus x squared occurs at x equals 50. So the width that maximizes the area is 50 meters. Now that we know x equals 50, we can substitute it back into our equation for y. That is, y equals 100 minus x, resulting to y equals 100 minus 50. This gives y equals 50, so the dimensions that maximize the area are 50 meters by 50 meters. In summary, to maximize the area with 200 meters of fencing, The rectangular garden should be a square with dimensions 50 meters by 50 meters. This gives us the largest possible area for the vegetable garden. Let's review the steps. When solving optimization problems, define the variables used. Set up the optimization and constraint equations. Use the derivatives to find the maximum or minimum values. And lastly, remember to check that your solution meets all the conditions given in the problem. Now let's move on to another real life scenario where we can apply our skills in finding derivatives. During the pandemic, many people lost jobs due to business closures, but some sectors like food delivery thrived to generate income. Maria started a business making food boxes. She aims to maximize her profit by minimizing material costs while keeping the box's volume and proportional dimensions constant. The box should have a base length 6 times its width and volume of 20 cubic inches. The material costs are 3 pesos per square inch for the sides and 15 pesos per square inch for the top and bottom. Help Maria find the box dimensions that will minimize the material. Let's break down the problem. Maria wants a box with a base length that's 6 times the width and a volume of 20 cubic inches. The material for the sides cost 3 pesos per square inch, while the material for the top and bottom cost 15 pesos per square inch. We need to find the dimensions of the box that will minimize the cost. To solve this problem, let's define our variables. Let W represent the width of the base, L the length of the base, and H the height of the box. Since the base length is 6 times the width, we can say L equals 6W. We also know that the volume, which is length times width times height, must equal 20 cubic inches. Our first equation is the constraint for volume. Substitute L equals 6W into the volume formula, and we get 6W times W times H equals 20. Simplifying, we have 6W squared H equals 20. Dividing both sides by 6W squared, it will yield 2 H equals 20 over 6W squared, canceling the greatest common factor 2. From 20 and 6, we have H equals 10 over 3W squared. This equation expresses height in terms of width, making it easier to work with one variable. Now let's set up the cost function. We have 4 lateral faces, 2 with area W times H, and 2 with area L times H, costing 3 pesos per square inch. Additionally, the top and bottom each have an area of L times W, costing 15 pesos per square inch. Using the formula for the surface area for a rectangular prism times the material cost, the cost function is given by C equals 3 times the quantity 2L times H plus 2 times W times H plus 15 times 2 times L times W. Substitute L equals 6W and H equals 10 over 3W squared into the equation to express the cost function in terms of W alone. After substituting and simplifying, we have a single variable cost function in terms of W, which is C equals 140 over W plus 180 W squared. This function represents the total material cost based on the width of the box's base. To find the width that minimizes the cost, we take the derivative of the cost function with respect to w and set it equal to 0. This gives us the critical points where the cost could be minimized. To do this, we use the following differentiation rules to get the derivative of each term. To get the derivative of the first term in C equals 140 over W plus 180 W squared, we let U equals 140 and V equals W. The derivative of U is 0, while the derivative of V is 1. Then applying the quotient rule for differentiation, f prime of x equals vu prime minus uv prime all over v squared. When f of x is equal to u over v, we get w times 0 minus 140 times 1 all over w squared. For the second term, we apply the differentiation rule. F prime of x equals nu raised to n minus 1 times u prime when f of x equals u raised to n, which will give us 360w. Simplifying this, we will have negative 140 over w squared plus 360w. We equate the function to 0, so we will have 0 equals negative 140 over w squared plus 360w. We solve for the critical value for w. Multiply the equation all throughout by w squared to eliminate the denominator of the first term, resulting to 0 equals negative 140 plus 360w raised to the third power. Adding 140 to both sides, we will have 140 equals 360w raised to the third power. Dividing both sides by 360, we will be able to isolate the variable w. Reduce the left side by extracting the common factor 20 from 140 and 360. We will get 7 over 18. We now extract the cube root from both sides to get the value of w. We will have the cube roots of 7 over 18. It is practical to convert the cube roots of 7 over 18 to decimal form. Using a calculator, we will have an approximate value of 73 hundredths inch. To confirm this critical point is a minimum, we apply the second derivative test. Remember that our goal is to get the box's dimension that will minimize the material costs. So, we check whether the second derivative at this point is positive. To do this, we get the derivative of the first derivative of the function. To get the derivative of the first term, negative 140 over w squared, we let u equals negative 140 and v equals w squared. The derivative of u is 0, while the derivative of v is 2w. Applying the quotient rule for differentiation, we get w squared times 0 minus negative 140 times 2w all over w raised to the fourth power. For the second term, its derivative is 360. Simplifying, we will have 280w over w raised to the fourth power plus 360, thus resulting to 280 over w raised to the third power plus 360. Analyzing the expression and considering the fact that w is always positive since it denotes distance between 2 points, the sum 280 over w cubed plus 360 is also positive. Hence, we say that the minimum value of the function occurs at W equals 73 hundredths inch. Now substitute W equals 7300 inch into L equals 6W and H equals 10 over 3W squared to find the optimal dimensions. For the length, we will have 6 times 73 hundredths, which will result to 4 and 38 hundredths. And for the height, we have H equals 10 over 3 times the square of 73 hundredths, resulting to a value that is approximately equal to 6 and 26 hundredths. We check if this will give us the volume requirement, that is V equals the product of 73 hundredths, 4 and 38 hundredths, and 6 and 26 hundredths. The product is approximately equal to 20 and 2 hundredths. Hence, the box's dimensions are 73 hundredths inch by 4 and 38 inches by 6 and 26 inches. These dimensions provide the lowest material cost while meeting the volume requirement, which is 20 cubic inches. In this lesson, we used calculus to solve a practical problem involving cost minimization. By defining variables used, setting up equations, using derivatives, and testing critical points, we found the best box dimensions for Maria's food business. Thank you for joining this session on real life applications of derivative of functions. Keep practicing to see how calculus can help solve real world problems. Enjoy learning!